Good evening. Uh, okay. So, what is it that makes flat earthing so seductive? I think it's what always makes bad ideas attractive, and that is they offer us an easy path, an easy way to kind of simplify. You know, we don't like to have to think too hard. We don't like to have to Um, sorry, I'm more presentable background. Um, we don't like to have to, you know, get into the brain and just rework the entire engine because then one thing or another stops making sense. Which is right. It's good to kind of get you know sensible ideas. To try and build from sensible ideas on your way up. Um, Flat Earth appeals to people for several reasons. One, they can and they can, well, one of them is that, you know, early chapters of the Bible basically present the earth as it is thought to be in the ancient Near East. And that is, as sort of a bubbled over sort of, flat area. And that's attractive to people from Mesopotamia, which is among which is a very flat region of of the earth. Like just flat for miles and miles. Um, One of the keys, though, is that these were people who didn't necessarily have an extensive experience of the world. In ancient times, it was, something to go 5 miles away from home. Most of people spent most of their lives within 5 miles, and in that range, it's like how much roundness of the earth do you actually encounter. So it's we live lives often according to what's intuitive to us. But, it's like you could see Mount Everest from someplace. You could see the sun all during the day if that's how you thought about it. A lot of people they think they can hide, the sun in vanishing points and in what's called linear perspective. Now, to demonstrate linear perspective, let me show you my cell phone. And you'll notice that on the screen, the angle of the screen that this takes up is less than the angle of the screen that this takes up. However, if I flip it over, look at that. They're about the same length. So it's the it's not that this part suddenly becomes smaller when I tilt it or this part longer. It's that holding it up to the camera, holding it up to, this viewing thing, as it goes back, the angles coming into the camera are the angles coming into the camera, the ones closer up, 1 degree of angle from this, it's going to be smaller here and larger back here. And that is, in essence, what linear perspective is about. It is about how, as you go backwards, what occupies a lot more, many more degrees of angle up here occupies fewer back here. Like what may be like that many degrees here, far fewer back here. And that's why things look smaller as they go back. Now you can, in a computer program, you could do what's called orthogonal, an orthogonal view, where everything is just seen um, at their exact size. So 5 meters here is the same as 5 meters here. So it's, you know it and you'll see that it all kind of lines up along that dimension. So we really have, you know, it's part of how we visualize, despite this being a monocular view right here. It's part of how you see that the painting um, bet- behind my left ear, that painting is actually bigger than my head, but it looks smaller than it from where it is, and that is your cue that it's deeper in the frame. Um, and you can also see right here the blinds, and as you can see that they kind of point back, and that if you continued the lines of all these things, they would eventually reach a point somewhere behind me, most likely at eye level. Um, and that's part of how we define eye level. But one of the keys here, one of the keys here, is to understand that some aspects of how we appreciate other dimensions of measurement are kind of reliant on these sorts of things. Uh, They think they can disappear the sun in it, but here's the question: how large does the sun have to be in order to be visible from across half the world? And to be visible not just across the world, but be visible at the proportion that we see it in the sky. How big does the sun have to be? And the answer is something like 50 miles. 50 miles worth of size. And you get something like that, and you put it, you know, several thousand miles away as it needs to be if it's going to go to the other side of the world in order to eliminate that side. Um, you get this sort of, you can get it to shrink somewhat, but you can't get it to just vanish. It's too big. You'd have to move it way, if the earth was flat and you were trying to make the sun disappear, you'd have to make it go way, 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 way over. And another thing that we would notice is that as it tracks across, it tracks across the arc of the dome of the sky as we perceive it, it never really changes how its angular diameter. It never really changes how big it is from sunrise to sunset. Now it may now there is a famous illusion with the moon, for example, that it, looks much bigger over the horizon than it does over our heads. But when we take objective measurements of it, we see that this is, well, just an illusion. It seems bigger to us, but if we do a objective measurement of it, if we kind of hold up the ruler to at arm's length and say, okay, this is how big it is over here, and this is how big it is over here, then you get uh basically the same size, which is odd for something that is supposed to be roving all over the disk of the flat Earth. And this is one of those things that breaks flat Earth. It breaks flat Earth basically because flat Earth has to obey the laws. It has to obey. I mean, these dimensions, this angle, this measure of angle of the sun. It's over there at this point because it's uh, al- almost, if not after sunset, or the moon, wherever it is at the moment. They're all basically they keep that same angular diameter, that same you know few degrees or a few fractions of a degree that it occupies across the broad sort of 360 degree in both directions sort of arc of the sky. It stays the same size wherever you're looking at it, and it only kind of wobbles from that when it's setting. And when it's setting, it's not sort of going like "Meow." It's not you know it's not getting smaller as it goes away. It is instead s- just maybe flattening out a little bit and dipping below the horizon. That's another thing. Dipping below the horizon. Now, let's see. Now, I want you to notice something. If we are at the horizon of something. Now, the way a horizon works is that everything above that horizon, every you're basically seeing anything that is shorter than has less elevation than your eye, your point of view remains below that point of view, remains below the horizon from your perspective. Because it is what you can see below you. The other part of the horizon, the other part of your scope of sight, things taller than that, you have to look up to. The angles have to go up from your point of view. Okay? And because of that, anything that is up higher than your point of view, your height of, anything that is above that, if you're looking up, even if you're looking up, it has to be taller. It has to be higher in elevation. And so if the sun was zooming around at a consistent altitude, just like that, if it was zooming around the earth like that, or over the earth, over the flat earth, it might change its apparent position in the sky, versus you. It might be over there or over there, but it couldn't really dip below the horizon of your supposed flat Earth because it is above your point of view. It has to be above your point of view, especially if it's 50 miles wide. You can't have this ultra hot plasma source or this ultra hot, fiery whatever you think it is. You can't have that, just a few thousand feet up. It would incinerate everything. Just like the myth of Helios's sun, Sun. Oh, not Sun, Son. Helios's child who asked his god father a favor. He wanted to drive the chariot, so the unsure hands of this amateur, he ends up, screwing up the job, and I think Zeus has to shoot down the chariot with a lightning bolt. And that's the end of him. So the key here is that you have to have it pretty high up, and you have to, you know it can't fall below the horizon because just like you look at what's at my you look at what where the vanishing point of the blinds behind me. You look at that, and they have to keep going in a certain direction, and they have to keep you know going basically towards that vanishing point, but they have to go at it from above. So if you have something that is visible, that is that big, and you just move it further back, like I'm moving this about, straight back, it's going to keep moving along the lines of perspective back that way if it's keeping a constant, altitude, you know? And you can see how my hand is moving pretty much along a line of perspective as I move it back and forth. So they misunderstand a fundamental part about how linear perspective works. And I'm not moving this up and down. You can see, like, particularly if I move along the top of the camera bag and back and forth like that, you can see that it's moving lower in the image, because this is kind of tilted up, but it is maintaining it's maintaining its altitude along a line, and it's just kind of, if you look at the lines, they eventually converge back there. But if you got something really big and that can be seen from just about anywhere, you could not hide it, in linear perspective. But then we have aerial perspective is their next thing. They say, oh well, the atmosphere around it will make it go away. And that's a you know the question is, we see the sun go from the horizon over there to the horizon over there, if we're looking at it and it keeps the same essential track going, it keeps the same size basically wherever you look at it, which is one issue because how does it keep the same size if it is going backwards in linear perspective? It would, you know, change size according to how far away it is, but it keeps the same size. Maybe it's that it's never changing its distance from us as our perspective changes on it. So we get a change in we get a change in the angle of our view of it, but not a change in the distance of our view of it. So it remains the same size and perspective. See how that works? The other thing is this notion of aerial perspective. What aerial perspective is, if you've ever been out on a foggy day, you'll notice that as you look into the distance, you you can see the you can see lights and objects grow dimmer and dimmer and more kind of fuzzed out, diffused as they go back until ultimately they disappear. That is what they're saying again accounts for, the sun disappearing below the horizon. But that doesn't have anything to do with that. And the reality is something disappearing below the horizon. Um, I mean, the how much? It's like for one thing, it doesn't vary that terribly much. You don't suddenly see the sun just disappear. I mean, you see it disappear behind the clouds. You see it. Um, you see it kind of get a little oranger, more reddish. The light begins to lose some of its more bluer and greener sort of wavelengths it but that's explainable as it's being seen not only through more of the atmosphere, but at some point it's being seen only through the refraction of the atmosphere, which is why the last parts of sunlight of the day, or the first parts of sunlight in the morning, are of a different sort of tone. But nonetheless, the sun shows up at the same places and at the same time, and there's nothing particular about the aerial perspective that leads that justifies flat Earth. But what else would it be? The apparent levelness of the ground. And they'll talk about how all the canals must be flat, all the lake surfaces must be flat, because otherwise, the how would things be contained? How would the lake be contained if it's curved rather than um, flat and surrounded by the rock? There, how can you curve that water surface? One of the things to understand is that rather than there being kind of, you got this one sort of dimension here and this other dimension here, and you get this sort of squared off sort of slice of Earth, and as you go down, it's another slice, it's another slice, it's another slice. Um, rather than see things in those terms, we have to realize that in a real way, a planet is a pile. It is a pile of material, but it's not a pile like you might see behind me or something like that. Um, it's more like a conical sort of pile. Sort of like, you know, you got sort of an arc of things. An arc, just as you have sort of these arcs of view coming out of your perspective. Well, you've got a pile of material, and that pile accreted, gathered more material to itself. And as it accreted more and more, gravity crushed everything down to the smallest possible shape. And when you got a whole pile of stuff, what's the what's essentially the smallest shape you can get? And the answer is a sphere, which we can establish as being in three dimensions, all points that have that are a certain radius away from the center. And it's not a perfect sphere. The rotation of the Earth is one part of why, and the imperfections of the material and everything of gravitational forces. That's another thing, but it's roughly spherical with a very small amount of deviation from that. And the key is to understand that the way this pile work is radial from the center of mass. Okay? So everything that's being drawn in is being drawn into it in a sphere. And this is part, this was kind of, I was kind of trying to figure out how to visualize it and how to visualize downhill and uphill when you have curvature to deal with. It kind of, makes our brains break a little bit because we're used to think of uphill and downhill from a relatively flat amount of curvature. You know, you looking a mile away, you have about this much. You have about this much curvature. This much. You think you can see this much? This much 8 inches of anything that terribly well from a mile away? No, you can't. It's a very small number of pixels, so to speak. It's a very small number of pixels. Up here, it takes up the whole screen, but back a mile away, back 5,280 of these, bop, 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 marching backwards in perspective. This is minuscule. It's at the limits, if not below the limits of human perception. You have to be looking many miles away in order to actually see all that much curvature. And that is part of it. That is part of understanding that curvature. But still, if you're looking at it in terms of like the whole course of the Mississippi River, or the whole expanse of Lake Superior, or the Caspian Sea, or the Mediterranean Sea, or the Atlantic Ocean, it's a fair question. How do you rationalize that? And the answer that occurred to me is to think in terms of layers of spheres, all stacked, that the pile that is Earth, you can see it in terms of layers and layers of spheres. And that when you move down a sphere, you're moving down in elevation. Down a sphere, you're moving down in elevation. Down a sphere, you're moving down in elevation. So you have the sphere that represents the height of Mount Everest, and then spheres going down and down and down and down towards sea level. And then you have the the spheres that go down and down and down from sea level to the Challenger Deep, to the deepest part of our surface. And then from there, you go down and down and down until the Earth's center. You know, and each part of this is a sphere. And so things want to move from the biggest sphere down towards the smallest sphere that they can. And that's both rocks, the atmosphere. It wants to get in as close as it can, to the lowest, sphere that it can physically, you know, get to. The water does the same, and the rock does the same, and the metals and whatever else. So if you look at it from that perspective, you can visualize layers of curvature of curved spheres, and that this elevation of a mountain and the elevation of the next mountain over that corresponds to that, and the elevation of the next mountain over that corresponds to that, and all the air in between them, we can look at that as being a layer in that sort of sense. And then we go next layer down, and it's got its own sort of, contours and profiles, and then down, and then down, and then down. And looking at things this way, seeing that sort of curved sort of layer, we can visualize a wide lake or a wide ocean as being contained by the rocks and the material that is at that shares its sphere. So the sea level sphere has certain rocks, certain soils, certain whatever, whatever's at that level, at that sort of sphere that contains the ocean. And you can see the same thing going on in all the rocks below it. Each one has their own sort of contour of that particular sphere of the planet. And so you pile up the spheres going up, and you can get um, this sort of sense of what contains what. And then you go up higher, and you can visualize the weather, you can visualize the atmosphere, and the other things doing the same thing. And this is useful because it trains our minds to think in terms not of sharing you know uh, a up and down height, and then a back and forth sort of dimension. We can see it in terms of a curve around the planet, and that curve that in within the planet we can see that sort of common level of elevation and understand what different things place in it is and how it keeps it, how Lake Superior's shores, though they're about 600 feet above sea level, how they contain Lake Superior without, the water overflowing you know, the curvature. Because the flat earthers, they want, I keep on seeing this again and again. They want to look at they want to see a universal down direction. They want to think of things in that way, that down in South America and down in Australia is the same thing as down in North America, down in Europe. They want to see both being the same direction because they don't want to see that these things can be brought to that there can be this sort of convergence at a point and that everything is being drawn towards that point. They want to see airplanes going in the sky, and they want to pretend like, oh, they have to keep on putting the nose down, putting the nose down, putting the nose down in order to keep it from flying off the globe. They want to see the water as just dripping off the globe. They want to see that because they want to simplify everything to something that their brains can process without much effort. So they want to see everything as if it's as if you can scale it down to the a demonstration in a room in that same gravity field, which has locally basically almost the same, like the number of degrees of separation for um if 8 inches worth of curvature is the curvature for if this is the amount of curvature over a mile, if this is the amount of curvature over a mile, and the divergence, the divergence 1 mile out of 21, 24,100 miles. I think that's about the circumference of the equator. Just think of how many how much of a fraction of a degree, just a foot's worth of difference is. That's why a lot of things appear to be flat because the 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 scale of this compass, if you will, the scale of that fan of 180 and then 180 more degrees is absolutely colossal. To get maybe 10 degrees, or let's see, if we're going to do 24, let's see what, let's see, we're going to go to, you know what, I can do this from my cell phone. Let's see. Okay. 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 So, so 24,100 divided by 360 is about 67 miles. So to get 1 degree of 1 degree of 1 degree of difference, and that is a ridiculously small, you know, angle. 1 degree of difference. It takes 67 miles. So what is 1 mile's worth of difference? Okay, so 24, no. 360 divided by 24,100. And that is 0.0149 and a string of digits. That's how many degrees we're talking about. So like a hundredth, you know, 14, 15 thousandths of a degree is all a mile will buy you. So, and what is that? Let's see. Go to that, and let's see. So, what is that? What is how much curvature is that for this? So, 15 thousandths of a degree divided by 5,280. You're getting kicked back many decimal decimal points at that point, which is part of what makes it non-intuitive. At our scale, the curvature is so small as to be unnoticeable. So this is part of why we need to kind of think in different dimensions. And I guess I've said what I need to say. So y'all have a nice day.